I recently uploaded a video of a three-dimensional fractal I rendered in Blender, and a bunch of you asked me how I made it. The fractal is called a mandelbulb, which is a three-dimensional version of the mandelbulb set. So in the first part I'll be explaining the history and the math behind fractals, and then the second part will be the Blender tutorial. If you want to skip the first part, just go to the timestamp on the screen now. The concept of fractal geometry has been around for a while, but the first time fractals really entered the public's conscience was on March 1st, 1980, when Benoit Mandelbulb rendered his equation for the first time. He based his formula on the works of French mathematician Gaston Julia, who came up with a similar equation more than half a century before Mandelbulb. Unfortunately, Julia would never get to see his work visualized, because to fully capture the detail of these kinds of fractals, you pretty much need a computer, because trying to draw on paper is nearly impossible due to its incredible complexity. That's why Julia could only speculate what this formula would look like. Even Mandelbulb was only able to render his formula because of his job at IBM, where he had access to very powerful computers. This all makes it sound like the formula is incredibly complex, but it's really not. The entire formula to create a mandelbulb is z equals z squared plus c. In this formula, z and c are complex numbers. So a complex number is a number that has a real part. This number could be any number that you could think of: negative numbers, positive numbers, fractions, anything really. The other part is called the imaginary number. Now this name doesn't really make sense because the imaginary number isn't imaginary, it has a value, which is the square root of -1. But because there's no real solution for the square root of -1, they just assigned it the unit I and called it imaginary. This means if we square I, we get -1. This is going to be a big part of the fractal. So to create it, we'll just make a normal plane and assign all the real numbers to the x-axis and all the imaginary numbers to the y-axis. Now any complex number has a point on this plane. So now what we can do is take any number from this plane and insert it into our formula. Now to get a result, you can try to remember how to solve an equation and how to simplify it, but that's a lot of effort. So I found this website that lets you solve complex equations and even shows you the steps it does, which is really interesting because it gives you insight into how the whole Mandelbulb set really works. So now if we insert our point into the z and the c of the formula, you'll see that the result is an entirely new point. Now the cool part is that we can take the result and replace the z in our formula with our new number, and you'll see we get another new complex number. And we can do this over and over again, iterating the formula. Now if you repeat this for all the points on the plane, you'll see that they all fall into one of two categories. Either it keeps moving away from its original point, towards infinity, or it stays within 2 units of its original position. Now to get the funky psychedelic colors you've all seen in the Mandelbulb set, all you need to do is color the points depending on how fast they move away from their original point. But we want to make 3-dimensional fractals. So on August 11th, 2009, mathematician Daniel White posted a blog post where he wrote about his discovery of a 3-dimensional version of the Mandelbulb set, and he called it a mandelbulb. Now to make this, he didn't use the traditional 3 axes x, y, and z to make the fractal, but he used spherical coordinates. These use 2 angles and 1 radius to describe the location of a point. Now these things look so cool, they've even been used in movies like Big Hero 6 or Annihilation, and you can also recreate them in Blender. To make the fractal, I'll use the newest Blender version 2.8, which is currently still in alpha, so expect at least a few crashes along the way. The reason I'm using this version is because it has a new render engine called Eevee. This lets us view the fractals in real time. I'll create the fractals using volumetric, so for us to see them in the viewport, we'll have to enable volumetric here. And under here you can see an option called volumetric shadows. This will help us a lot later on because it will let the volumetrics interact with each other, so it doesn't just look like an amorphous blob, but actually like a solid object. We can ignore the rest of the scene for now, just keep the cube and open up the shader editor. Basically, we just need to replicate the formula from the blog with math nodes. So to get the x, y, and z variables like in the formula, we need to create a texture coordinates node and a separate XYZ node. Plug the object into there. So we have our X, Y, and Z. Now the first component we need is the row, which is basically just the distance every point has from the center of the scene. This is also known as the length of a vector. So to get the length of the vector, we need to create a math node and select power and type in 2 so we square the number, and we want to repeat that for the X, Y, and Z. And add them all together. And then you need to get the square root of the whole thing in the end. To get the square root, we can take power again, and because the 0.5 power of any number is also the square root of the number, so we can just keep it like that. And now this is the length of the vector of every point in the object. So we can just take all of this, make a group node by pressing Ctrl G and plugging it into the output and typing in vector length. This is just for clarity so we can see what we're doing. And we can name the group vector length. And this is also our row, so I'll just make another node group and call it row, just to keep track of what we're doing. Now the next part is theta, which we'll need another separate XYZ node for. And now we just do the same thing, we replicate exactly what we see in the formula with math nodes. Now we can turn this back into a node group again and call the output theta and call the whole node group theta, just to keep track of what we're doing. Now we need to make phi. The same thing again, separate XYZ node, and just try to replicate the mathematical operations with math nodes. So we need a divide and an arctangent. For the arctangent node, you can just leave this value at whatever you want, because adjusting this value doesn't affect anything at all. Node group again, put that into the output, call it phi. And now you have yourself the components you need to make spherical coordinates. Now an important part of the formula is the n, which basically determines how many bulbs the big bulb has on the outside, so how many, I guess, blossoms it kind of has. So to make a placeholder for that, we can just add a value node. This will be our n. And something we need to use over and over again is row to the nth power. So we'll just create another math node, power, and put row on the top and n on the bottom. There you go. So now we'll make the x, y, and z parts of the formula. So again, we'll just have to recreate all of the operations with nodes. Now this will be our x component, and to make a node group out of this, first I'll create a reroute here by shift left clicking and dragging to create this little socket. This is helpful because if I didn't make that, it would create two inputs for the n, which we don't want. So this way you can see this is inside and it only has one input there, if that makes sense. Now you can name the inputs. And in the panel here on the side, which you can, by the way, open and close by pressing N, you can enable color. You can make it red, just to make the whole thing look a little cooler. Now the Y component is almost the same, So we'll just copy that, and to make sure that we don't overwrite it, you can press this little 2 to make this its own user. Then you can type in y and make it green because y is green. Now the only difference between the x and the y is that the cosine here is also a sine. Now we can rename the output to y. There you go. Now you have your x and your y. All we need now is our z, which is the shortest of the 3. So we're almost done with all the math nodes. Make a node group again, call the output z, and the inputs here are, we have our n and our theta. Theta's in the bottom, so we can theta, and this one n. There we go, so that's our x, y, and z outputs. Now to finish this off, we'll just need to multiply the x, y, and z with our power r up here. And now we can combine this all back to a vector. Now because this is the main part of our formula, we can turn this all into another node group. So let's just take this over here. Shift left click again to reroute so we can get it all nice and clean. And select all those parts, press Ctrl G, put this into the output. Now this is the output of our Z component in our formula. So this is the thing we'll keep plugging back into the next iteration like we did with the Mandelbulb before. So we can just type in Z there. And the inputs are going to be N and Z. So basically the way we'll do it is we'll copy the node group over and over again, plugging the Z output into the Z input again and again. Now if you remember in the two-dimensional formula, in the end we added the C back onto it, so to do that, we'll add a vector math node and add the original point back onto it like that. Now it's a good idea to make another node group out of this because we'll be needing a few more inputs and outputs to get this to do what we want. So this vector is our C, so I can rename that to C. Now we'll need to add a limit input, which basically decides how far a point is allowed to move until it's not inside our bulb anymore. So we'll just add, just drag that into there. No, I guess not. It's difficult because if we add another one, it makes this vector input, which is not what we want. We just want a value input, so we'll have to remove that and add something with just a value input here. It sucks. I wish you could change the type of input each socket is, but you'll just have to live with a workaround like that. And this is going to be our limit. Rename that to limit. We'll need a length and a iteration counter. Now to the iterations, we'll add 1. Now this gets interesting when we copy the node group over and over again, and it keeps adding 1 onto the iteration counter, so it knows exactly how many iterations it has done, and we can color the different points according to how many iterations it took it to move a certain amount, which gives us the cool psychedelic colors again. So we'll just add 1. Now when the distance of the point after it's iterated is further away than our limit, we don't want it to be inside our bulb anymore. So we can decide that by taking our limit and adding a less than node. You have to put the limit in the bottom there. And this returns a value of 0 if a point is less than the limit, and a value of 1 if it's more. So if we multiply this, with our iteration counter, it basically just gets rid of all the values that are outside of our limits. Anyway, so this is our iteration, so we can plug this into the output again and call this iter. And to get the distance of every point from the center of the scene, we'll just add our handy vector length node we made earlier by going to the group right here and adding our vector length. If you've named it like I have, you can just plug the output of the add into there, and this will then be our vector length. Sure, we can just call it length. Sure. And now we want to keep the limit and the C, and then this is going to be our Z, the output of the add is going to be our Z, and then we want to keep the N here. So now let's sort all of these like we have on the other side, so it's going to be easier to copy the whole thing. And that's basically it. Now we just need to iterate it by copying this over and over again and plugging the outputs of one into the inputs of the next one. So let's do it about 5 times first to test it, see if it works. Make sure not to mess it up like I did there. Plug the right outputs into the right inputs, otherwise you'll get a mess in the end. So now all we need is a volumetrics node and plug the iterations into the density and plug that into the volume output, not into the surface, into the volume of the material output. And now let's adjust the N to about 8, and right now in Blender 2.8 adjusting this doesn't do anything, so you'll have to add a value node to be able to adjust inputs here, which is a little weird. They'll probably fix that pretty soon, hopefully. So now if we render this by pressing Shift Z, we can see an amorphous blob. Now this looks like crap because the lighting sucks at the moment. So if we move our point light we have here a little closer and increase the strength, you can see something happening in there. Now to get rid of this outside mess here, you can add a greater than node, math greater than, and plug the iteration into there and turn, let's say 3.5. And there you go. Now you have your mandelbulb isolated. At the moment this looks very low quality, so let's just move the camera a bit closer just to see it. And then you can adjust the tile size here to 2. Now you can see you get much finer detail around the edges there. So to get it looking a little more dense, you can add a multiply node and turn that up, and there you go. Now you have it looking a little more solid. You can turn the background off. Now this is where the creative part comes in. You can now just adjust the light to whatever you want. I'll just make some area lights. Now the way you can animate this, like I did, is by adjusting the N value over here. With higher values you get a lot more little tiny bulbs on the outside. With lower values you get less bulbs on the outside. To get better quality you should adjust the start and end, because that basically tells Blender how far away from the camera it should look for volumetrics. So if we turn this down to as small as possible without the bulb completely disappearing, you'll see that the quality is a lot better. Another important part in making this looking good is adjusting the shadow samples, because you can see if it's very low, it goes back to looking like an amorphous blob and not like a beautiful fractal. So if you turn this higher up, you can actually see the detail emerging again. And this seems to have fixed our lighting problem a bit. Now to make the cool colors, to give it some cool colors and not just a white cloudy look, we can add a color ramp. If we adjust the color ramp to HSV, hue saturation value, and change this to far, make it red and blue, you can actually see you have yourself a little rainbow. Now if you take the length output and put it into the color, it's starting to color itself. And you can see it looks kind of like a nebula or something. It's a pretty cool effect actually. I had slightly different settings for the one I used for the video. I think I had this one a little more purple, and this one blue. But you can see you can play around with this forever and find new cool looking ways to make this. But basically, that's how you make a mandelbulb in Blender. You can use the same technique of replicating formulas using math nodes for basically any geometrical equation you can find out there. So I hope this was at least a little helpful. And if you ended up making something cool with this, I'd love to see it. You can send it to me on Twitter or in the comments below. If you don't want to go through the trouble of creating all these math nodes and everything, you can just download the original file for the video I made in the description below if you just want to play around with it or create your own cool effects.